Hello students, in the last class we have studied about the geometrical isomerism. Geometrical isomerism in coordination complexes. Coordination number complex of the type coordination number 4 and the complexes which are having coordination number 6. In the today's class we are going to study about the optical isomerism. What is optical isomerism? Or optical isomerism is also called as enantiomerism. Optical isomers or enantiomers are pair of molecules or ions which are non-superimposable mirror images to each other. Optical isomers are enantiomers. These are a pair of molecules which are non-superimposable mirror images to each other. The condition for optical isomerism is the molecule should be chiral or asymmetric, or it should not have a plane of symmetry. Chiral molecules are optically active because they rotate the plane polarized light as it passes through the solution. Chiral molecules are optically active because they rotate the plane polarized light as it passes through the solution. When we pass a normal light into the Nicol prism, we are going to get a plane polarized light where the all particles are in a or aligned in a same direction. When that light is passed to the chiral molecule, it rotates the plane polarized light either to the right side or to the left side. Depending on that, there are two isomers. When the plane polarized light rotates to the right side, then it is called as dextrorotatory. It is represented by D or plus. If the plane polarized light is rotated to the left side, then it is called as levorotatory. It is represented by L or minus. The essential condition for the substance to be optically active is it should not have a plane of symmetry. The optical isomerism in a coordination number 4 complexes. Optical isomers in a coordination complexes which are having coordination number 4, or it is bonded with the 4 ligands. The complex with the coordination number 4 either square planar or tetrahedral. They have a structure either square planar structure or a tetrahedral structure. Generally, square planar complexes do not show optical isomerism because they have a plane of symmetry. Since they have a plane of symmetry, square planar complexes will not show optical isomerism. But some of the complexes, square planar complexes which are having a larger or bulkier ligands may show optical activity because of the distorted structure. Because of the bulkier group, the structure is slightly distorted. Because of that, it may show optical activity. For example, isobutylene diamine, mesodiphenyl ethylene diamine, palladium. This complex shows optical activity because of the bulkier group. Here you can see the bulkier ligand. Because of this bulkier ligand, it show optical activity. And then next one is tetrahedral complexes. Tetrahedral complex of the type Ma4, Ma2b2, Ma3b3 type do not show optical isomerism due to equivalent arrangement of ligands or a metal ion. Their arrangements are equivalent, therefore they will not show optical activity. But the complex of the type MABCT, where all the 4 ligands are of different types, it shows the optical activity. You can see the example here. Central metal ion is arsenic, and it is having a ligand sulfur, methyl, ethyl and benzoate group. It may rotate a plane polarized light either to the right side or the left side. If it is rotates to the right side, then it is called as dextrorotatory, and the next second compound is levorotatory. These are non-superimposable mirror images. Therefore, these exist as a pair of enantiomer, or they are also called as geometrical isomers. Optical isomers. Tetrahedral complex of the type beryllium 2 boron through zinc 3 with unsymmetrical chelating ligand. Unsymmetrical chelating ligand. Chelating ligand means they form a ring-like compounds. They show optical activity. For example, bis benzoyl acetanato beryllium. Okay, because of the larger chelating group, it shows optical activity. Okay, you can see the structure here. These are a pair of enantiomers. One is dextrorotatory and another is leo-rotatory. In the first one, you can see here it is having C double bond O and single bond O here. Here it is having single bond and double bond. These are non-superimposable mirror images. Therefore, they are called as optical isomers. Next one is optical isomerism in octahedral complexes. Octahedral complex having coordination number 6 because 6 ligands are attached to the central metal ion. Ma4b2 type, Ma4bc type, Ma3b3 type are optically inactive and they do not show optical isomerism because of the plane of symmetry. They have a plane of symmetry, because of that they are optically inactive. Ma2b2c2 type, MABCDEF type, MAA3 type, MA8Y2 type, MAA2AB type, MAA2B2 and MAB3 type exhibit optical activity or they show optical isomerism. Generally, cis-isomers are optically active and trans-isomers are optically inactive because trans-isomers have a plane of symmetry and cis-isomers are optically active because they do not have a plane of symmetry. Cis-isomer means the same groups are adjacent to each other. Ma2b2 type. First one is Ma2b2 type. A is one kind of ligand, B is another kind of ligand and C is another kind of ligand. This type of complexes have a 6 geometrical isomers. When we write in the last class we have studied, this type of complexes have a 6 type of geometrical isomers. Out of these 6 type, only one kind of isomer shows optical activity, which are having all similar groups cis to one another. Geometrical isomer with all like groups or same groups cis to one another occur in a 2 optical isomers but not all geometrical isomers. Yes, you can see the example. In this, ammonia adjacent to each other, or pyridine, chlorine, these two like groups are cis to each other. It do not have a plane of symmetry, because of that it has a optical activity. One is in a D form, another one is in L form. This one is a cis D isomer and this one is a cis L isomer. Okay, these are a non-superimposable mirror images. Therefore, they are called as optical isomers. These are example which are having Ma2b2 C2 type of complexes, but these arrangements have a plane of symmetry. Okay, these arrangement we can see here, this has a plane of symmetry and this also has a plane of symmetry and plane of symmetry. Because of the plane of symmetry, this will not show optical activity. Next one is MABCDEF type, where all the 6 ligands are different. Okay, these type of complexes gives 15 geometrical isomers. When we change the positions or geometrical arrangement of the 6 ligands, we get 50 geometrical isomers. Each one of shows optical activity. All the 15 geometrical shows optical activity. In total, we get 30 optical isomers. Each one shows optical activity. Each one has a pair of enantiomer. Therefore, we get 30 optical isomers. For example, one example is here. Platinum, which is having pyridine, ammonia, NO2, chlorine, bromine, iodine ligand. Okay, it has a optical activity. These are a pair of enantiomer. One is a dextrorotatory. One isomer is a dextrorotatory and another one is a leo-rotatory. Next one is MAA, three type of complexes. AA means it is a bidentate ligand. In each bidentate ligand donate two pair of electrons. Okay, three bidentate ligands can donate six pair of electron. Due to the absence of plane of symmetry in this complex, when we see the structure of this complex, it is not having a plane of symmetry or a center of symmetry. Because of that, this exists in a enantiomeric form, that is D form and L form. These complex always exist in a pair of enantiomeric form. It is also noted that an octahedral complexes containing three chelating rings are always optically active. Okay, when we write the structure of these complexes, it form a ring like compounds. Since it has a bidentate ligand, it forms a chelating ligand or a ring like compounds. These type of complexes always optically active. Okay, you can see here example. In the first example, ethylene diamine is a bidentate ligand. Here one ethylene diamine, another ethylene diamine, and the third ethylene diamine. Okay, and this isomer, when we write the another isomer, which is the L isomer, these two are optically active. Second example, chromium trioxalato. Okay, we are having a oxalate ion as a bidentate ligand. Okay, it also is optically active. The first one is a D isomer and another one is a L isomers. These the ligands or the complexes which are having three bidentate ligand or the complexes which are having a chelating ligand are always optically active. Next one is MA twice A2. Here there are two bidentate ligand and two monodentate ligand. This type of complex exists as a cis and trans isomer. Here cis isomer is a chiral and optically active. The trans isomer is achiral and optically inactive. Cis isomer means here the atoms are where the identical groups or identical atoms are adjacent to each other. That complex is optically active and chiral, and the trans isomer is chiral and optically inactive. When you see the first example, okay, here two chloride ions are adjacent to each other, and nitrogen is adjacent to each other, and N is adjacent to each other. This type of complex is cis-isomer. It's a dextrorotatory, and another mirror image is always levorotatory. It exists in a optical isomers, or these complex is optically active. When we see the trans isomer where chloride are opposite to each other and two ethylene diamine groups are opposite to each other because of the plane of symmetry. Because of the plane of symmetry or achiral molecule, this is optically inactive. Next one is MAA A2B2 type. Here it is having one bidentate ligand and two types of monodentate ligand. Here also cis isomer of this type complex optically active but not trans isomer. The complexes which are having the cis isomer is optically active and the trans isomer is optically inactive. Why trans isomer is optically inactive? Because it is having a plane of symmetry. In the first structure is example having cis isomer, ammonia cis to each other, chloride is cis to each other. It is not having a plane of symmetry. Because of that, it is optically active, and this complex is dextrorotatory and then one is levorotatory. In this structure, ethylene diamine comes here, ammonia is here, and chloride ions are here. It is also cis isomer, but it is levorotatory. These are pair of optical isomers. Okay, there are two types of trans isomers are possible. Okay, this is one trans isomer and this is another trans isomer where the molecule is having a plane of symmetry. It is having a plane of symmetry. Because of the plane of symmetry, these trans isomers are optically inactive. When they have a plane of symmetry, their optical activity gets cancelled. Therefore, they are optically inactive. In the next one, MAA to AB type, there are two bidentate ligand and two single monodentate ligand. In this complex also, cis-isomer is optically active due to the absence of plane of symmetry but not trans-isomer. The reason is same. All the cis-isomers are optically active because they do not have a plane of symmetry, and the trans-isomer is optically inactive. You can see the example here. Okay, here two different monodentate ligands are there. In such cases, we have to see the differentiating ligand, that is a bidentate ligand. This bidentate ligand, the heteroatom is nitrogen. Nitrogen is cis to each other. Nitrogen is cis to each other. Therefore, this is called a cis-isomer. This is a dextrorotatory. It has a mirror images, that is Leo isomer. Okay, we can write it as a central metal atom cobalt. Ammonia chloride comes here, and the ethylene diamine molecule come this side. These are a pair of optical isomers which are non-superimposable mirror images. They are optically active because they do not have a plane of symmetry. When we see the trans isomer, they have a plane of symmetry. When we cut the molecule into two equal halves, we get the same parts. Therefore, they are achiral and they are optically inactive. Next one is MAB3 type. This type of complex exists in a cis and trans isomer. Each of these form optically active, as we have seen in the first MA3 type of complexes which form a chelating complexes, or they are chelating ligands. Such ligands always exist in a optical isomer or pair of enantiomeric form. Okay, it is also bidentate ligand, but is unsymmetrical bidentate ligand. Unsymmetrical bidentate ligand means you can see here glyoxinate is a bidentate ligand. Glyoxinate is a bidentate ligand which is having nitrogen and oxygen. In ethylene diamine, both the donor atoms are same. Ethylene diamine, the donor atoms are nitrogen, both are same. But here the donor atom, one is nitrogen, another is oxygen. Such kind of ligands are called as unsymmetrical bidentate ligand. These bidentate ligand form a ring-like structure, or they form a chelating complexes. Such isomers are always optically active, and hence they give a pair of enantiomers or optical isomers. Okay, you can see here, this is one isomer. This is one isomer. This is a facial d-isomer, or it is also called a cis d-isomer. Facial means here the same kind of heteroatoms are in a one trigonal phase, and another three atoms are in another trigonal phase. You can see here nitrogen, three nitrogens are in a one trigonal phase, and then three oxygens are in another trigonal phase. Such complexes are called facial isomers, or they are cis isomers. And this compound is dextrorotatory, therefore it is written as face D isomer, cis D isomer or facial D isomer. Another isomer is in a Leo rotatory form. Okay, therefore it is written as face L isomers. Next example, Mer isomer, or it is a trans isomer. Cis isomer also show optical activity, and trans isomer is also showing optical activity. Okay, trans isomer means trans or mer isomer means here the nitrogen atom or one kind of the atoms are present at the plane bisecting the complex. Okay. Okay, this is the plane. This is the plane which bisect the molecule. The 3 nitrogen atoms are present at the plane bisecting the molecules. Another 3 or meridian of the complex. This type of complex is called as trans or more isomer. Okay, this is also optical activity because it is not having a plane of symmetry. This is one more D isomer and another one is a more L isomer. Remember that the complexes which are having bidentate ligand or the complexes which are having chelating ligand, either it may be cis-isomer or trans isomer, it always shows optical activity. Okay, this is about the optical isomerism. Optical isomerism of the complexes which are having coordination number 4 and coordination number 6. You have to practice and write the complexes. This is the last topic of the coordination chemistry. From the next class, we are going to start with the next chapter, that is organometallic chemistry. Thank you.